Hey everyone. Ever wonder how your favorite streaming service seems to just know what movie you're in the mood for? Or how an online store suggests a product you didn't even know you needed, but now you absolutely have to have it? Well, a huge part of that magic is a machine learning technique called data clustering. And today, we're going to pull back that curtain and demystify the whole thing. But before we get into all the techie stuff, let's start with a little thought experiment. Just imagine you've been handed this massive, overflowing box of Legos. They're all mixed up, every color, shape, and size you can think of, the whole shebang. And here's the catch. You've got no instruction manual. So what's your first instinct? I bet you just start sorting, right? You'd make a pile of red bricks over here, a pile of blue ones over there, maybe put all the little wheels in a corner. And that impulse, that need to create order out of chaos, that's the very heart of clustering. You know, that simple act of sorting Legos without a guide, it unlocks one of the coolest ideas in all of AI, unsupervised learning. See, normally with supervised learning, you basically spoon-feed a machine examples. This is a cat, this is a dog. But with unsupervised learning, it's like you drop a mountain of data in front of the machine and just say, here, go figure it out. It has to learn by pure observation, finding the hidden structure all by itself. And that brings us right to the star of the show today, data clustering. It's right at the center of this unsupervised world. And at its core, it's all about one simple but incredibly powerful idea, grouping similar things together. So what is clustering, really? Well, there's the textbook definition for you. But honestly, I just think of it as finding the natural tribes or communities that are hiding in your data. It's like looking at a big crowd of data points and figuring out who hangs out with whom. Okay, so here's a really important point. It's super easy to get clustering confused with another machine learning task, classification. With classification, you start with boxes that are already labeled. Think spam or not spam for your email. The goal is to train a model to put new emails into one of those existing boxes. But with clustering, you don't have any boxes to start with. The whole point is for the algorithm to find the natural groupings and create the boxes for you. And this quote, it absolutely nails it. This is what a perfect clustering result looks like. If we go back to our Legos, every single piece in your red brick pile is, well, a red brick. They're all super similar. That's high similarity within the cluster. But that pile of red bricks is very, very different from your pile of wheels. That's low similarity between clusters. That's the dream. Tight, clean groups that are obviously different from each other. Okay, but wait a second. This brings up a pretty huge question. How does a machine, which only gets numbers, have any idea what similar even means? For us, it's totally intuitive that two red bricks are alike. But for a computer, it all comes down to math. And specifically, it comes down to the idea of distance. Now, there are a bunch of ways to measure distance, but let's talk about the two big ones, Euclidean and Manhattan. Euclidean is the one you probably remember from geometry class. It's just a straight line between 2 points, the shortest path possible, the classic as the crow flies. But Manhattan distance is different. Imagine you're in a city, like Manhattan, with a perfect grid of streets. You can't just fly through buildings, right? You have to go along the blocks, up and down, left and right. That's Manhattan distance for you. Let's make this totally concrete. Here are two data points on a graph. Let's call them point A, at coordinates 1, 2, and point B, over at 3, 5. Now, how far apart are they? Well, as we're about to see, the answer completely depends on which path you're allowed to take. Okay, so first up, Manhattan distance. We're on our city grid. To get from A to B, we have to go 2 blocks to the right from an x-coordinate of 1 to 3, and then we have to go 3 blocks up from a y-coordinate of 2 to 5. So you add those up, 2 plus 3, and you get a total distance of 5. Easy enough, right? Now for Euclidean. We're the crow, flying in a perfectly straight line. We get to use the Pythagorean theorem here. So it's the square root of that horizontal distance, 2 squared, plus the vertical distance, 3 squared. You crunch the numbers and you get a much shorter distance, about 3.61. And here's the big takeaway. The way you choose to measure distance can totally change which points the algorithm thinks are close, and that can completely change the clusters you end up with. So we've got a handle on how to measure similarity, but how do we use that to actually build our clusters? Well, there are a ton of methods, but they mostly fall into two main approaches. And I love this analogy. Think of it as the organizer versus the manager. First, let's meet our meticulous organizer. This is hierarchical clustering. This method doesn't just toss your data into a few buckets. Oh no, it is way more careful than that. It builds a complete family tree of your data, showing you exactly how every single point is related to every other point at every single level. And our organizer here has two ways it can work. It can go bottom up, which is called agglomerative. This starts by treating every single data point as its own tiny little cluster. Then, step by step, it merges the closest pairs together, and then merges those new clusters, and so on, until everything is in one giant supercluster. Or it can go top-down, which is called divisive. This starts with that one giant group, and then intelligently splits it and splits it again until every point is all by itself. And the payoff for all of this incredibly detailed work is something really cool, a diagram called a dendrogram. It's not just a chart, it's a whole visual story of your data's structure. You can see exactly at what distance different groups merged, which gives you this incredibly powerful tool to explore your data. All right, now for our second personality. K means clustering. This is our efficient manager. This approach is all about speed, efficiency, and just getting the job done. But it asks for one thing from you up front. You have to tell it exactly how many clusters, that's the K, you want it to find from the get-go. So how does our efficient manager work? It's a pretty elegant four-step dance. First, it just takes a guess. It randomly drops K pins on your data map. These are the initial centers, or centroids, of your clusters. Then, step 2, it assigns every single data point to whichever pin it's closest to. Step 3, and this is the clever part, it looks at all the points in each new group and recalculates the center. So the pins move. And finally, it just repeats steps 2 and 3 over and over again, reassigning points and moving the pins until the groups settle down and the pins stop moving. So, which one should you pick, the organizer or the manager? Well, it really depends on what you're trying to do. If you're just exploring a brand new data set and you have no idea how many clusters might be in there, hierarchical clustering, our organizer, is a fantastic choice. But if you have a massive data set and you need an answer fast, and you have a pretty good guess how many groups you're looking for, then K-means, our manager, is probably your best bet. It's all about picking the right tool for the job. Okay, so we've had a really fun dive into the mechanics here, but let's talk about the so what. Why does any of this matter? Because this isn't just some abstract theory. Clustering is a total powerhouse that is quietly shaping the world all around us. So where is this stuff actually being used? Well, it's pretty much everywhere. When you get one of those scarily accurate movie recommendations, that's clustering, grouping you with other viewers who have similar tastes. When your bank sends you a text about a suspicious transaction, that's probably clustering. That's identified a charge that just doesn't fit your normal spending patterns. It is the hidden engine behind so much of what we do online. Now, as powerful as all this is, it's not a magic wand. There is still some really tough, interesting challenges to solve. I mean, how do you do this with datasets that have billions of points? How do you find clusters that aren't just simple circles, but might be shaped like a banana or a long string? These are the kinds of questions that data scientists are tackling every single day. And it's what makes this field so dynamic and exciting. So, let's wrap this up. We've seen that clustering is this amazing tool for finding hidden patterns in data without any prior labels. We've looked at how we measure similarity and how our organizer and manager methods build those groups. And we've seen how it's already changing things in the real world. Which really just leaves us with one final and, I think, pretty exciting question. In this age of big data, with information being collected everywhere all the time, what incredible hidden patterns are just sitting there waiting to be discovered? Thanks for watching.